Day number 2 of unexpanding, aka factoring. Recall from last day that factoring using the greatest common factor undoes the distributive property. So in doing your homework, textbook work, in looking at your work from expanding, you should see that those are just forward and backward operations. And today we're going to do the same thing, but today we want to undo binomial multiplication, binomial expansion, also known as FOIL. So binomial is 2 terms times 2 terms. How many terms did we originally determine when we expanded a pair of binomials? Well, we always got 4. And then we usually combined like terms and ended up with 3 or 2. If you're not sure about this, what I suggest you do right now is go back and look at your either video notes or your classwork. So here's an example of binomial multiplication using an array model. And again, the basic idea is it's a 2-level. If I used the word FOIL, they would occupy these spaces right here. All we want to do is break a difficult problem into a simpler problem, look at each piece separately, and in organizing it this way, something really nice happened. Our like terms were always diagonal from each other. And when we organize this, here's what we see. Again, there are like terms, so we always got 4 terms, and then we were good students and we collected like terms. And again, in my picture, the like terms were always diagonal. The x squared term was always in the top left, and the numerical, or the other thing, was in the bottom right. So given that today we want to undo that, what we want to end up with is when we unexpand, when we factor something, we want to end up with 2 binomials. So again, the key idea is when you multiply 2 binomials, you always get 4 terms. Therefore, when you unmultiply them, you should get back to your 2 binomials. So here's a question. Can we factor this polynomial using a greatest common factor? If we could, well, we could do it pictorially, and what I hope you recall from greatest common factor is greatest common factor, the rectangle always looked like this. It didn't look like the 4 square thing above. It looked like this. And what we would try to do is we would try to break this thing apart by finding the greatest common factor, that would be our vertical piece, and then finding out what each value of the top would be. And what I hope you see here is every term, the first 3 terms, have an x in common, but the last one doesn't, therefore x is not a common factor. Common factor has to be good for all of them. If you looked at the numbers then, 5, 3, 15 have something in common, but they don't all have anything in common, and in fact the x squared term has a 1. So if we were trying to factor this using greatest common factor, the only thing we would get for our GCF is 1, and 1 is a useless factor. 1 is a useless factor. 1 is the only useless factor in all of factoring. If we're going to look at this algebraically, well, algebraically what we would do is we would break each one of the pieces into its prime factors, and this one's pretty straightforward. And what we would end up with is this. And again, going through and highlighting, you cannot highlight something that is similar in every one of those terms. And again, what this says to us is greatest common factor does not work. But what I hope you would notice then is there is no GCF for all 4 terms, for all, but, and this is a really, really important but, some of the terms share some of the terms share things in common. So share things in common. So for example, if we just looked at some terms that share things in common. So for example, x squared and 5x have an x in common, and x squared and 3x have an x in common, and 3x and 5x have an x in common, and 5x and 15 have a 5 in common, and 3x and 15 have a 3 in common, but x squared and 15 have nothing in common. And by factoring using a GCF, this is the big stumbling block. But that doesn't mean we cannot factor that polynomial. It just means we can't use the greatest common factor. So we need to know a way of undoing a polynomial like this example right here that has 4 terms. And again, what I want you to realize is you have seen this polynomial when you have expanded. When you have expanded using the binomial property or FOIL. We've got an answer that looked like that, but then of course we collected like terms. So that's where we're going. So here we go then, factoring polynomials with 4 terms. Here's the example we're just talking about above. Well, we can create an area model. We can create an area model like we created when we expanded out 2 binomials. And if we put things in the right place, it becomes quite straightforward to look at 4 little mini problems that brings the entire problem together. So again, the habit I want to get into is putting the x squared term in the top left. I want to put my like terms diagonally across from each other, and whatever the last thing is goes there. In particular case, it's a number. And all I want to do now is look at this area as the area as a whole in 4 separate little pieces and figure out the dimensions of these 4 separate little rectangles inside. So it's nice to start right here because the only way we can get an area of x squared is x by x. And if this dimension of this piece is x, then this dimension also has to be x, and this also has to be x. So what I can then do is go, okay, well, if I know that the vertical dimension that I've highlighted yellow is x, what is this dimension? What times x is 5x, and that's 5. Similarly, if I know this dimension is x, then I know this dimension is x, and this dimension is x, because I know properties of rectangles. And if I know that, if that dimension, if the horizontal dimension is x, then the vertical dimension has to be 3x. And the only thing that I really haven't been concerned with right now is this little box down here, but what I can do is I can leave that as a final check and make sure that my pieces work out. And in fact, 3 times 5 is 15. So what I've done is I've used an area model to find the dimensions, the entire dimensions of a rectangle. And here they are right here. And if you don't believe that a rectangle with an area of x squared plus 5x plus 3x plus 15 has dimensions x plus 3 by x plus 5, all you have to simply do is multiply out those 2 binomials and you will get back to our start. So pictorially it's pretty nice, it's pretty straightforward. Algebraically, it's a little tricky. First thing we're going to do is we're going to look at 2 parts separately. So again, here's this idea of 2 by 2 grouping, the technique. We make 2 groups of 2. Now, it matters which 2 groups of 2 you make, and there's different combinations. And I'm just going to look at this one initially. Now, I can't do this with the video, but imagine I only want to look at this left pair. And I've put my hand over the right pair. What I want to do is look at the left pair, and now I want you to realize that, hey, we do have a common factor. And the common factor turns out to be x. And we'll use our GCF technique that we did last day, and we will factor out an x, and the remaining piece is, the remaining stuff is our other piece. Okay, so I factored that as much as I can based on that idea that we talked about right here. This idea of, well, some things have something in common. Okay, well, let's look at the right-hand pair. And we do the exact same thing. And we go, okay, we're going to break this into its pieces, 3 times x plus 3 times 5. And what we want to realize is they both have a 3 in common. In fact, it's a positive 3. So we can factor out the positive 3, and whatever's left over goes in brackets. It's our other factor of that piece. Now what I want you to really realize is, again, magically, not magically actually, algebraically, what we've done is right here we've generated a greatest common factor. It wasn't there before. We did a bit of algebraic manipulation and we got it. And now what we can do is we can take that out. Remember, that's not a subtraction, it's really a division, and whatever's left over goes in brackets. And what I want you to recognize is those answers are exactly the same. One, we've done it pictorially, and one, we've done it algebraically. Ultimately, I want you to decide which one you like the best. So let's look at the key ideas of both methods. The key ideas in the area model is, in order to do this successfully, we need to put the terms in the right spot. Again, there's 4 terms, there's 4 spaces. We need to put them in the right spot. Now in class, we're going to do some examples where we put them in the wrong spot and see what happens. And the other key idea is that what you can then do is you can look at each section, each of the 4 sections separately. And again, that's nice. Breaks a difficult problem into easier problems. Okay, the key idea algebraically is we need to break the polynomial into, again, I'll use the same word, in the right pairs. And then we're going to factor by greatest common factor. Okay, let's look at another example. Factor this polynomial completely. So again, there are 4 terms, and I'm going to fit it into this picture. I'm going to put my x squared term in the top right. I'm going to put my like terms across from each other. And I'm going to put the last thing right there. And now I'm going to go ahead and find out what the dimensions of each little piece have to be. And much like with GCF, if we determine the first one, then what I'm saying is x has to be a factor of the top right square area, and x has to be a factor of the bottom left as well. And again, we go through our logic we did above. X times x is x squared. X times what is 3x? Well, that's 3. X times what is xy? Well, it's y. And finally, we haven't even bothered with the last one, and now we just make sure everything works out, and if it does, we've done this right, and in fact, x times, or y times 3 is in fact 3y. So what that tells us is the dimensions of the rectangle that give us this particular area are x plus y times x plus 3. We have found the factors. We have found the 2 important pieces that when you multiply them together, you get back to this ugly expression. Okay, let's look at this example algebraically. Algebraically, we break this into 2 groups of 2. That's where the name comes from, 2 by 2. 2 times 2 is 4. We look at each piece separately. Again, I'll speed up a little bit. We factor that. They have a common factor of y. X plus 3 is left over. Again, what we've done is we've algebraically generated our LCD, or sorry, our GCF. Too many letters. we factor out the greatest common factor, and whatever is not highlighted goes in brackets. It's our other factor. And again, notice that these two answers are exactly the same. They're just done pictorially or one algebraically. Okay then. So here's our question. When you try to factor a polynomial using 2 by 2 grouping? Well, when do you try to do that? When greatest common factor will not work. So what we're learning factoring techniques. We have to look at a question and decide what technique that we have learned will we use. So when the GCF will not work, we might use 2 by 2 grouping, but then here's the big kicker, and there are 4 terms.